To my talk. Today I will talk about synthesizing programs in multi-level IR. And this was also joint work with my professors. So basically, first I want to motivate the whole thing. Why do we want to synthesize programs in MLIR? So given we have this C program that's just like some loops, and we want to compile it to be really fast. We could now go and compile it with LLVM 03, and it will give us a base performance, 1.0x. We could also use Poly to optimize it for memory and parallelism, and this would give us 5.6x. And this is about what we can get on LLVM IR level. But you see, like the plot goes up to 1000x. So I will now show you how we can reach that. We could go and we could rewrite the program in a higher level DSL, like the ln-alg IR dialect. And here we don't have encoded like the concrete order of the whole thing, but we have a very abstract way of describing the computation, and therefore the compiler can optimize it better. However, we see we still have like memory transformations, but actually this operation is a tensor contraction. And if we would rewrite it in like an even higher level dialect, the HLO dialect, we would get even higher performance of 200x. In fact, we can also offload it to an accelerator that runs HLO, and we get over 1000x speed up, which is really high. And now the big question is, how can we achieve this automatically? Because we don't want to rewrite all our code that is in C or like some loops to these higher level DSLs. And there's these approaches are called raising approaches. And yeah, today I will basically show one raising approach that can target different dialects automatically. But first, what is a raising approach? A raising approach takes a source program and takes target dialects and produces programs in these target dialects. The requirements we have on such approaches are that they are fast, that they are robust. So robust means they don't just match canonical forms of loops, but also like match closer to the semantics and less on the syntax. And they also should be automatic. So we don't want to write rules for every operation and for every dialect, because we would end up with a huge amount of raising rules. And traditional approaches that are currently there in MLIR rely on pattern matching. These are, of course, very fast. However, they are not so robust, as I will also show later in the plots. And they are also not automatic, because rules have to be provided for each operation, for each dialect manually. And actually, the synthesis approach, if we use synthesis, we can achieve complementary properties to that. It's not as fast because it's search-based. However, we can rapidly speed that up, as I show later. It's more robust because we match on rather like the semantics and the observations we get of a program. We match on the behavior and not the syntactic level. And also it's automatic, given that we can use the target dialects that are available in MLIR as a grammar and search in the space of the grammar for the programs. So now I first want to give you an idea how the tool that I have built works. I called it mlirSynth, and then I will show you some results that we got with this. So again, here's like the input-output formulation. We have a source program and a set of target dialects, and we synthesize programs in that target dialects. First, we pre-process the source program, and here we split out small problems that can be synthesized. Next, we run for each of these problems synthesis pass, basically, and the synthesis pass also takes the target dialect definitions and constructs a grammar, basically extracts a grammar out of them, and then searches in the space of the grammar. When we have completed all the synthesis subproblems, we do, we basically merge the solutions into a single function, and then we are done. We have synthesized the function. And finally, we validate the function because we want to know that the transformation is indeed true and is basically okay for all inputs. And finally, we get the program. First, the preprocessing. So this is a kernel function extracted from PolyBench with polygeist in the affine dialect. And we first identify some candidates in this, or some loops that can be raised to a high-level language. In this case, so we have just a simple heuristic, we detect functions that are, or like regions that are affine loops and perform operations on memrefs. So in this case, we have two regions, and now we outline these regions into separate functions. And each of these functions represents a separate problem where we can run our synthesizer. And yeah, the synthesizer knows what functions to synthesize by this property, by this attribute that we have. And finally, we also scale down the functions so we can run the search faster. What comes next is the synthesis. The synthesis is basically a search that searches for a program that meets a specification, and in our case, the specification is the behavior of a program. So we generate some inputs for each of the synthesis problems and track the output, and we then search for a program that meets the output, basically. And for that, we use an algorithm, a known algorithm, bottom-up enumerative search, where the main idea is that we keep a set of program candidates and combine program candidates to more complex ones. So initially, we start with very simple programs, just returning arguments and constants, and basically traverse the operations of the target dialect and combine operations, basically all candidates in all ways. And this will give us new candidates that we add to the candidate set. And each time we also evaluate the program. Yeah, we see how it behaves, and if it meets the specification, we terminate the search and found the program. We also do some optimization techniques that are really needed in this search. First, we do type correct by construction. So we check what are the operand types of an operation, and only consider candidates that meet this operand type. Also, we don't consider candidates actually in the set, but we consider observations, unique observations in the set, because several candidates could produce the same observation, and for example, in addition, and that reduces the number of candidates quite a bit. And also, we use polyhedral heuristics for guiding the search. Now that we have synthesized the individual functions, we now combine them back to a function by just doing an inlining operation, and then scale the problem back to its original size. Now we have basically found a function that is observationally equivalent for one input. But now, a good question is if it's equivalent for all inputs. So we basically searched using this evaluation technique because it's really, really fast. And but we now really want to know if the transformation is valid. So we take the candidate program that we found and lower it to the same language as the source program C, and also resize it. And then we run a bounded model checker that can give us several equivalence guarantees for all inputs. And we run it using float point arithmetic, permitting a small delta, because there can be rounding errors when you reorder float point operations. And we also check for integer arithmetic. And of course, we have the tested I/O equivalence. And in the end, the user can specify what requirement he needs, and then the replacement can happen or not, basically. Now we evaluated this tool on PolyBench. PolyBench is the polyhedral benchmark suite containing of kernels of several categories, and we selected 3 of these categories that contain programs that can be mapped to high-level linear algebra languages like HLO and linalg. In total, we have 15 programs. Now we evaluated what existing raising methods can do, which are rule-based, kernel-fairer, and multi-level tactics, and we see they can get 53%, like up to 53% in total of this benchmark. But our method can get, by using this search-based approach, we can get 93% of these kernels and raise them to HLO operations. Here's the performance that we can achieve with the raised operations. We evaluated first we raised it to HLO and compiled it with XLA, and we get a geomean speed up of 25x, which is quite significant. However, one example we couldn't raise, it falls back to the default performance. Then we also lowered it to linalg and compiled it with ERI, and ERI follows a different code generation strategy in this case, and we get a speed up of like 10x, and ERI is also faster in one of the kernels, basically. And all these numbers are in geomean larger than Poly, the state-of-the-art loop optimizer for LLVM. Now, an interesting question is, of course, the time it takes to synthesize, because as I said in the beginning, this is a disadvantage of the search-based approach. And actually the time it takes is dominated by the number of operations that are in the target program. And for example, this 3mm kernel contains 3 matrix multiplies that can be perfectly split out in 3 subproblems and contain 1 operation each. And here we can find the solution really fast, in a fraction of a second. The same goes for Deutschgen, which was our motivating example. And in the other cases, we have here 2 operations. It takes also under 1 second. And here on the left-hand side, we actually have kernels that have way more operations, up to 5 operations. Like, for example, the Circ kernel has 5 high-level operations, or the largest subproblem has 5 operations, and so it takes up to 10 minutes to find the matching kernel here. So yeah, future work. Ideally, so what I imagine would be making it practically usable in a compilation, end-to-end compilation flow. You just run the compiler, pass mlirSynth, program C, and it will raise it automatically, use domain-specific compilation, speed it up. But for this, we need to improve the method and also the applicability. For the method itself, we need to make it faster. And for that, I'm currently evaluating neural models to learn heuristics and speed up the search. Also, we need to detect code regions that can be raised not run it on too many regions of the program. Also, we need to make it more applicable, because right now it's just working on affine programs, but there are programs that can be mapped to high-level operations, but they are not affine. So maybe moving it to LLVM-IR. And of course also supporting more dialects in the target space. So there are more DSLs that we could target in MLIR and automatically raise to. Okay, that's it. Thanks.
Thank you for a very interesting talk, as usual. Please find the microphone if you have some questions.
Hi, that's a very nice talk. I do have a question. So have you considered another approach by, say, first converting your C program into Linear? And that conversion may not be very efficient, but that gives you something to start with, and then you can mutate the Linear programs and to hopefully give you something better than the original translation.
I think that would move the same problem just one level up, right? You would still have to find, starting from the linear generic level, the named operations, I think. And and in my experiments also the linear generic operations itself didn't end up in code that was as fast as the named operations. Because in the named operations, you can, if you identify, for example, a matrix multiply, you can apply, like vendor libraries and make it run faster. Yeah.
Thank you.
Mm-hmm.
Hi, nice talk and great project. I wonder, you mentioned downscaling. How do you select the sizes when you downscale?
These sizes. How I select, so basically I follow a scheme according to the prime numbers when I downscale, and so does it answer the question?
Yeah, is it possible that your smaller scale computation would be different because, for example, on I+7 access somewhere or that kind of stuff?
In theory, that would be possible, but in the benchmarks that I considered, that wasn't the case. There were no conditional statements in these kernels, and so
thank you.
That would not be an issue.
Thanks for the nice talk. I just wonder, how did you select the I/O? Did you randomly select, or did you use some, for example, the I/O come up with a library?
There are just selected, I basically randomly generated inputs for the function and recorded the output. But I recorded the inputs also in a range. So they were not hitting nearly like the maximum possible values of floats and doubles. But I generated them in a certain range from 0, 100 to 100. Yeah.
Okay, so what would be the success rate of your synthesis procedure? For example, maybe after your synthesis, in your evaluation, the equivalency evaluation procedure, maybe some of the I/O breaks. What would be the success rate of your synthesizer?
Can you repeat or revert the question a bit?
Because I think in theory you cannot guarantee your synthesis procedure is always correct, right? I just wonder how the success rate of the synthesis.
Okay, but we after finding, so we basically just use I/O checking or observations on when searching the program, but not when checking the program. We also check the program that it is equivalent to the source program for all inputs, and not just for one concrete example.
I see.
Yeah.
I see. Thank you.
Okay. Hopefully a short question, but could I have my next speaker come up and set up while we answer this? Thank you.
Okay.
So great talk, by the way. So I was just wondering that you, since you mentioned that you are currently targeting a limited set of dialects, so do you in theory, is it probable that this will work for all different dialects with all different designs and semantics, or will you potentially get problems there?
So the dialect needs to have a lowering to like affine and LVM, and I think that is the only constraint on the dialect. And I basically parse table gen files, so in theory I could support all dialects, but but there might be some engineering problems currently, but in theory, yes, I can support all of them. Yeah.
Thank you.
Great. Thank you much. Let's thank our speaker again.